Hello, my name is Aniko Bezur and I direct the Technical Studies Laboratory at Yale University's Institute for the Preservation of Cultural Heritage. I have the pleasure of introducing the next segment of the study day, which will be followed by a 30-minute break. We learned a lot from our previous speakers about the historical and cultural context of the three sets of Tarocchi cards, including their commissioning and ownership, the games played with the cards, and the relationship between their imagery and contemporary fashion. The upcoming talks will be switching gears and delving deeply into the materiality of Tarocchi cards, the stuff they are made of, and how their makers manipulated and combined these materials to create these miniature masterpieces. Each of the observable and measurable physical and chemical characteristics are just a second here, I'm having PowerPoint problems. Each of the observable and measurable physical and chemical characteristics of these cards are the result of choices made consciously or subconsciously by their makers. These choices may reflect their individual preferences, skills, and idiosyncrasies. Were they left-handed or right-handed, for example? Did they color within the lines, or did they deviate from a planned composition? Zooming out a bit, material choices can reflect the practices of a larger workshop to which a maker belonged, the state of technology in the making and application of paint, thin metal foils, and paper, and the larger availability of materials. Technological choices, however, cannot be separated from the socioeconomic and cultural context of the makers, commissioners, and users of these objects. The tastes of those who commissioned these sets of cards was informed by their place in society in the city-state of Milano and the broader regional politics. The political reality also impacted trade relations, along with the movement of craftspeople, among other things. It is because of these interdependencies we find it vital to bring diverse viewpoints together, as we are doing today and throughout this project. The following speakers are scientists representing 4 different institutions. I chose the Fortitude card for my introduction because of the many challenges conservators and scientists face and continue to face in carrying out research during the pandemic that requires in-person collaboration and the relocation of Tarocchi cards from their home institutions. Richard Hark, conservation scientist at Yale's Institute for the Preservation of Cultural Heritage, will start off this session with an overview of the scientific approaches used to study these amazing 15th century objects, while also ensuring their safety and preservation. In the second presentation, we will turn our attention to the analysis results, starting with the paint layers and the pigments and dyes responsible for their colors. This talk will be presented jointly by scientists at the Metropolitan Museum of Art, the Center for Conservation and Restoration of Cultural Heritage, La Venaria Reale, the National Gallery of Art in Washington, and Yale's Institute for the Preservation of Cultural Heritage. As a reminder, during the talks, please submit your questions and comments using the Q&A button at the bottom of your screens so that we may address them during the session starting at 2:15 p.m. You may also email questions to viscontitarocchi@gmail.com if we run out of time to address them today. And now I hand the screen over to Richard Hart.
Good morning. It is my distinct pleasure and challenge to briefly review the methods and instrumentation that our multi-institution team of scientists and conservators use to carry out technical analysis of the Tarocchi cards in several collections.
XRF, RTI, PMF, RIS, XRD, MFT. My goal is to help you make sense of the alphabet soup of the analytical techniques. I hope to provide you with a broad overview of what information we learn from each type of analysis and how it allows us to answer important questions as we compare cards from 3 separate decks. Technical analysis of art objects does not always involve such an extensive and thorough campaign, but this ongoing project serves to illustrate the complementarity of multiple scientific tools and the synergy that can develop when curators, conservators, and conservation scientists collaborate. In order to answer questions about the material and techniques used to create the Tarocchi we studied, it is necessary for you to have a basic understanding of the structure of these cards. While we tend to think of paintings in general as 2D objects, they of course have a third dimension. This schematic cross-section illustrates the layers that exist in the cards, which are just a little over 1 millimeter thick. Our goal was to examine each of the materials used to make a card, including the pigments, which could be colored minerals or organic dyes adsorbed onto an inorganic substrate, binders used to hold the pigment on the card, glue used to paste together the paper support, or the delicate metal leaf used to decorate these beautiful objects. While we obtained physical measurements of the width, height, thickness, and even the mass of the cards, most of our work had to do with using various types of light to interrogate these objects. Even now, after the advent of sophisticated instrumental methods, people examine art by closely looking at the object with the naked eye, either with direct lighting or by using raking light to gain a sense of the surface topography. To the trained eye, this can afford an incredible amount of information, such as the order of application of colorants, pigment mixtures, the nature of brush strokes in a painted surface, as well as evidence of aging and retouching. However, the Tarocchi cards are works in miniature, and this exercise benefits from the use of a stereo microscope, as illustrated with this series of images. Increasing to a magnification of 100x, where the finest details can be seen and careful comparisons made. What we see, with or without the aid of a microscope, is based on the image that is formed on our retinas when light is reflected from the object back into our eyes. However, with the use of instrumentation, we are not limited to using only visible light or relying solely upon the reflection of that light to visualize an art object and learn about its component materials. Light can interact with matter in a variety of ways, as shown in this slide. For example, in addition to reflection, some photons or particles of light can be absorbed by a material, while others are transmitted through it. In some cases, the color of light emitted is changed through the interaction with certain materials. This is known as fluorescence. Different types of information can be learned by measuring what happens to light when it interacts with matter. Using light to probe a substance is called spectroscopy, but this is not limited to just light that the natural eye can see. As you know, white light is a mixture of all the colors of the rainbow. The human eye can only perceive this relatively narrow portion of the electromagnetic spectrum illustrated here. The response of materials like pigments to wavelengths of light beyond the visible range provide a means for discriminating between different colorants. This is essentially a machine-enhanced, close-looking activity. Let me illustrate. Ultraviolet light, which people associate with the source of a summer sunburn, has a shorter wavelength and higher energy than visible light. While we cannot see light in the UV range, butterflies and certain insects can. This slide compares the response of the Empress cards from the Yale and Morgan collections in visible and UV light. You can see that the various colors in the cards respond somewhat differently in the two types of light, with some pigments displaying weak UV fluorescence. This multispectral technique can be carried out with the use of a modified digital SLR camera and the appropriate set of filters and light sources. Infrared light is likewise not visible to the naked eye without the use of night vision goggles. However, certain species of snakes, such as this pit viper, have an organ that allows them to sense the heat given off by nearby prey. As with UV light, the spectral response of pigments differs. Some materials absorb infrared light, while others transmit or reflect it. This allows the IR light to pass through the overlying paint layers down to the materials that lie below, sometimes revealing preparatory underdrawings, and allowing the identification of pigments and other materials. If one of the red, green, blue channels is replaced in the visible light image, the resulting so-called false color IR or false color UV images can aid in recognition of individual colorants or mixtures. Instead of just using several wavelengths of light to visualize an object, we can use a special camera, such as the one shown here on the left, to obtain a spectrum of every point on a Tarocchi card at one time. In this powerful and non-destructive approach, an image is obtained at wavelengths spaced a few nanometers apart from the visible to the infrared. The stack of these images is called a hypercube, which is the reason one of the names for this spectroscopic technique is hyperspectral imaging. Using sophisticated algorithms, it is possible to not only recognize the spectral response of each colorant in a Tarocchi card, but also its distribution throughout the image. As shown on the right, each of the various spectral end members correspond to a unique pigment or pigment combination. More on the results we obtain using this technique will be given in the next presentation. What about the use of X-rays to study the Tarocchi? Can any animals see in this region of the electromagnetic spectrum? Well, I know of only one, and he unfortunately was not available for this project. More seriously, the transmission of X-rays, like a dental or medical X-ray, allows one to visualize the location of pigments. Lighter elements are relatively transparent to high-energy X-rays, while heavier atoms such as gold, mercury, and lead absorb them. The image formed is therefore based on the radio opacity of the materials in the cards, with heavier elements appearing brighter in the image, as illustrated here for the Yale Empress card. This approach can be useful for seeing the distribution of pigments, finding hidden portions of a work, changes in composition, or pentimenti, and retouching areas. We can also use X-rays to identify the elements present in the Tarocchi using a technique called X-ray fluorescence spectroscopy, or XRF. In this approach, an incoming X-ray knocks an electron from one of the orbitals surrounding the nucleus within an atom of the material. A hole is produced, resulting in a high-energy, unstable configuration for the atom. To restore equilibrium, an electron from a higher energy outer orbital falls into the hole. Since this is a lower energy position, the excess energy is emitted in the form of a fluorescent X-ray. The energies of the secondary X-rays are characteristic for each element. A single element can produce multiple peaks, as recorded in the XRF spectrum obtained from the female Knight of Swords. This approach is non-destructive. While one can perform XRF at one or more single points, it is also possible to scan across the surface of a Tarocchi card to obtain element maps from multiple elements at one time. The spacing of measurement points for many of the scans we carried out on the cards is 90 micrometers, or about the thickness of a human hair, providing a spatial resolution of nearly 300 dpi. This generates over 2 million XRF spectra per scan and allows us to infer the identity and distribution of pigments based on the elements present. This method, known as macro XRF spectroscopy, is even more informative when combined with other techniques such as reflectance imaging spectroscopy. In this slide, we can see a visible image of the female Knight of Swords and 3 false color elemental maps generated by macro X-ray fluorescence spectroscopy. In these maps, areas that are lighter or brighter in color indicate increased levels of an element, while the darker or black areas indicate a lower concentration or the absence of that element. You will learn what these interesting element maps reveal in subsequent presentations. In this project, we used several different XRF instruments, some of which were portable and could be used for scanning as well as point measurements. The cards had to be carefully placed to ensure their physical safety and to be certain we obtained data for just Tarocchi and not background material. In addition, all personnel using X-ray generating equipment had proper radiation safety training. Macro XRF can tell us what elements are present on the cards, but it cannot identify the specific colorants. It is also of minimal value when trying to identify the binder used to adhere the paint to the support. However, there are other approaches that allow us to more specifically identify the pigments and binders present. It turns out that molecules and the atoms in crystalline material are constantly moving, undergoing vibrations as represented here. The energy required for each type of stretching or bending motion is in the infrared region of the electromagnetic spectrum and is characteristic for the particular combination of atoms involved. We can use infrared and Raman spectroscopy to measure this energy in a non-destructive manner. The Raman spectra obtained from two areas of the love card are shown here. The data collected from the Tarocchi cards is compared with spectra of known samples to identify the species present, such as the ultramarine and vermilion shown here. Some colorants give weak Raman signals, while some samples display substantial fluorescence interference. One way to dramatically enhance the intensity of the Raman signal is to remove a tiny sample, chemically treat it, and then add a drop of a solution containing silver nanoparticles. This approach is called surface-enhanced Raman spectroscopy, or SIRS, and is especially helpful for the identification of organic lake pigments and glazes, as you will shortly see. Pictured here are our colleagues in Italy performing analysis with a portable Raman spectrometer on the left and an infrared microscope on the right. Both techniques were carried out directly on the cards, and the results nicely complement the data obtained using macro XRF and reflectance imaging spectroscopy. The reflected IR measurements were used to get an idea of what types of binders were present, but additional tests using various forms of mass spectrometry are being carried out to obtain more definitive identification. Let me conclude with a brief mention of two more techniques. Question: is there anything we can learn about the glue that was used to paste together the paper to create the card support? The paper wrapper covering the edges was worn away on several of the Yale and Morgan cards, allowing us to take very tiny samples of the adhesive, which had the appearance of a proteinaceous hide glue. While non-invasive methods are always preferable, some information can only be obtained by taking small samples. We sent the samples to a colleague, Daniel Kirby, for peptide mass fingerprinting, or PMF, analysis. This approach uses the unique genus or even species-specific nature of the collagen protein found in skin to distinguish between different animals. Collagen, whose name comes from the Greek meaning glue-producing, makes up about a third of the total protein mass in animals. It is composed of 3 polypeptide chains that combine to form a triple helix. In PMF, the polypeptide chain is cut at specific locations into smaller peptides using an enzyme. The mixture of pieces is analyzed using a mass spectrometry technique called MALDI, which gives the mass-to-charge ratio of the resulting fragments. Comparison with a library of known samples allows for identification of the animal source. Marie-France Lemay will later describe the interesting results we obtained. How can we compare the decorative punch work that was done in the gold and silver leaf found in the Tarocchi? The answer is yet another 3-letter method. With reflectance transformation imaging, or RTI, an object is placed under a half-dome framework containing an array of lights arranged at different angles to the surface of the object. A camera takes multiple visible light images as each light is activated and then turned off in turn. A compilation of these images is transformed into an RTI file that allows the viewer control of the angle of illumination to better visualize the surface texture as shown here. I've removed the color component of the raking light images of a close-up of Empress to allow better visualization of the tool marks. While this tour of techniques has been necessarily a rapid ride, hopefully the results that my colleagues will share in subsequent presentations will be somewhat more meaningful now that you have an idea of how they were obtained. Prepare to be amazed.
Hello, everyone. I have the pleasure to introduce the first collegial presentation for today and to tell you how everything started. In January 2020, in the framework of the Mass Network Initiative for Conservation Science, the NICS, we received a proposal from the Morgan Library regarding the scientific study of one of their treasures, the 15th century Tarocchi cards. In its early stages, the project involved Morgan's conservators, the NICS conservation scientists, and Yale's scientists, conservators, and art historians who were already working on their own cards. We only had one chance to meet all together at the Morgan to look at those incredible artworks, and then the pandemic hit. The project finally kicked off in April 2021, and now here we are telling you about our findings. Object of the technical study have been 36 cards from the Visconti di Modrone deck belonging to the Yale's Beinecke Library, 38 from the Visconti-Sforza deck, 23 of which from the Morgan Colleoni collection and 15 from the Carrara Colleoni. And recently, the Brera-Brambilla deck from the collection of the Pinacoteca di Brera has been included in the technical study, as Letizia also mentioned, so this presentation won't include results on this deck. All decks are characterized by the same color palette, simplified here and reported. In this presentation, we will show you how different pigments were used to obtain similar color effects. The manifold goals of our study go from the technical characterization of the cards preparation to their illumination, the gilding technique, and the decoration, the materials, and so on. The expected outcome is a substantial contribution to the conversation about attribution, integrating art historical information with evidence based on materials and painting techniques. A significant result of the analytical study is the identification of the color palette used by the artist to illuminate the cards. Our presentation will focus only on the characterization of the pigments and binders used to create the color palette. The list of analytical techniques and acronyms might be overwhelming for most of you, but we wanted to give you an idea of the approach we put in place. Richard has already described most of them, and you know now that by their combination, we were able to see fine details otherwise impossible to notice. We obtained the images illuminating the cards with different wavelengths in order to see through layers of paints. We could even identify chemical elements in every card, inferring the presence of possible pigments, then confirmed by other techniques. What you see here are the 16 cards from the Morgan Colleoni collection studied at the Met. 13 are figural cards and 3 are pip cards. All the cards have a painted outline framing the illustration, blue for the figural, red for the pip cards. Both inorganic and organic pigments contributed to complete the color palette. And in this first part of our speech, we will focus on the inorganic pigments. Then we will continue on to organic materials. One of the most effective techniques we use not only to determine the pigments, but also their distribution all over the cards is the macro X-ray fluorescence spectroscopy, which allows to detect chemical elements present on an artwork surface and illustrate their distribution. And now I will show you some of our results. What you see here is the result of the scanning. It is basically a different way of looking at the cards. Here it is the distribution in particular of the chemical element mercury. Mercury is the main constituent of the red pigment vermilion, a common historical pigment made of mercury sulfide, and mapping its distribution helps to highlight if and where vermilion was used, confirmed then also by Raman spectroscopy. Vermilion is the main pigment used for the juggler's clothes, and it is also present in the frames outlining every card, even though it is often covered by a blue line, as you can see from this micrograph. There are cards where the red line is missing, like in Temperance and Fortitude, two of the replacement cards. And this is in fact reflected in the XRF map, where you see the mercury missing. Vermilion was also used to define details on the skin, like on the hands of Fortitude. Detailed high-resolution scans illustrate even better the use of vermilion to define details in the skin and add a three-dimensional effects, like you see on Hope from the Visconti Modrone deck. This short animation shows you how we proceed when we want to attribute elements to a specific color and use. The overlap of the mercury maps over a black and white image of the cars clearly shows where the pigment was used. The chemical element lead, whose distribution is represented here in white, is widespread and its intensity has a correlation with the type of pigment containing lead. In fact, a chemical element can be a component of more than one pigment, as in this case. Where high concentrations of lead overlap white areas on the cars, the use of lead white could be hypothesized, and it was in fact confirmed by Raman analysis, a technique that gives you the fingerprint of pigments, allowing an accurate identification. This series of images better shows you what I meant. The top of the platforms in the Pope, the King of Staves, the King of Swords, and the Queen of Swords is white, as well as the horses in the chariot, some figures close, and the background of the pip cards. The handling of lead white is similar for Yale cards as well, although the use of lead white painted background for the pip cards is unique to the Morgan set. However, sometimes lead does overlap to yellow colors, like in the seats of the chariot and the King of Staves, the hare, and many other examples. Lead-containing yellow paints result rich in tin, here illustrated in yellow. The simultaneous presence of lead and tin in the yellows indicates the use of lead tin yellow as pigment. This pigment was discovered in the 13th century, and it became of common use in the 15th century. Tin has also been detected in white areas, indicating a possible mixture of lead white and lead tin yellow. Lead tin yellow was also used for fine lines and details, like for the painting flowers and blade of grass, as shown here by the map of tin on the grass of the lover's card. Combining elemental maps is crucial to identify different pigments, as in the case of the lion in Fortitude, where a high concentration of tin does not correspond to lead, which is indeed almost absent except for a few details. Only the integration with other analytical techniques help to identify this brown pigment. And in fact, micro X-ray diffraction, another technique to identify compounds or materials, and Raman spectroscopy again, tell us that this brown has a crystalline structure of a tin sulfide called burntite, known in art as mosaic gold, an artificial pigment that was used after the 14th century. The pigment was also, as I said, identified also by Raman spectroscopy. Mosaic gold is not the most common brown used on the tarot cards. It has been detected on some replacement cards like Fortitude shown here, and also on the feet of the star from the Carrara deck. Mosaic gold was not used in brown colors of the Yale's deck. As an interesting side note, this pigment has been identified by scientific analysis of the painted Stuttgart cards deck, dating to 1430, which is one of the earliest surviving packs of playing cards. A different brown color, more in the shade of a yellow-brown, is used mostly for details, like to define curves in the hair or to outline details on clothes, or even on the seats or horses. Iron is the main component found in these browns, and it possibly indicates the use of an iron-containing earth, like yellow ochre, once again confirmed by Raman spectroscopy. Iron is a common chemical element in many pigments, including red iron earths, like red ochres, iron oxides, like hematite, or even certain blue pigments, like smalt. This explains the reason why you see so much iron on these maps, but we are going to focus only on these brown details. Let me show you here an example of what where a high resolution XRF mapping was done on a small area. Here's the Lion of Fortitude from the Visconti di Modrone deck. You see the use of lead tin yellow for the lion skin by the overlap of lead and tin maps, and the use of a yellow ochre to define the curves of the mane, represented here in the arrow map. The blues are quite complex, and we identified 3 different blue pigments used alone or combined, as Marcy will show you in a bit. This is the distribution of cobalt, the main component of several blue pigments. In the Morgan's card, cobalt overlaps with other elements not reported here, like potassium, manganese, iron, lead, and arsenic. All these elements found in the same pigment indicate the use of smalt, a light blue glassy pigment. Smalt was used in combination with other blues on clothes or to simulate the dazzling shine on arms and armor. The Morgan cards liberally use smalt as a colorant for blue pigments, while little or no smalt was used on the Yale cards.
While the Morgan cards extensively use smalt as a blue pigment, we also see the use of lapis lazuli and azurite for blues in both the sets of cards. Roxanne will follow up with more discussion of lapis lazuli, but I wanted to take a moment to discuss azurite, a copper-based pigment, which you can see throughout all of the cards scanned. And the distribution of copper is seen in blue on the screen for several of the Clone cards. And what you'll also see is that there is copper signal associated with the green areas, such as the grass in the foreground, because of another copper-based pigment, green malachite, which I'll discuss in due course. To expand on the use of the different blue pigments between the Morgan and Yale cards, the Morgan cards show the use of smalt as a blue pigment either alone or in combination with azurite and lapis lazuli, sometimes even within the same card, as you can see here in the Colonne's Last Judgment. The blue on the horns are shown only copper, hence azurite alone, whereas the blue of the sword shows only cobalt or smalt, whereas the gown of God seems to be done in a mixture of the two. And the use of smalt in the Morgan Colonne cards is peculiar. When we see them in association, azurite seems to be painted above as a layer with smalt, where smalt is on the bottom, and you can see that in the micrograph, where the lighter smalt is below the richer, brighter azurite. In contrast, there is little or no smalt being used in the Yale cards, and this might be related to the dates of the cards and when they were created. Smalt started appearing more widely in Italian painting in the 15th century, although it first appears even earlier than that. The Clone cards are believed to be created a decade or more later than the Modrone cards, which could correspond to a wider availability or preference for smalt as the pigment was cheaper than azurite due to the advancement in glass manufacture. This highlights how the changes in the materials at the time, at that time in history, can be reflected in these two decks of cards. Additionally, we've seen different mixtures of azurite being used based on the presence of a trace amount of barium in the azurite paint. This is a known trace element seen in azurite mixtures that relates to the azurite mineral source. And we've been tracking the ratios of barium in the azurite in both sets of cards, and this is a part of a larger study comparing azurite mixtures in different types of objects from different European locations from this time. And you can see on this slide that while barium is detected in some of the blues in the Morgan cards, such as the Robe of Time, the harness and details in the chariot, and in the Pip cards, it is not present in all of them. For example, it is notably absent in the blues in the Wheel of Fortune or in the Queen of Coins. As areas of the blues on both the Yale and Morgan cards were compared to see how the amount of barium to copper might be grouping. And so we plotted them on a binary graph showing the amount of the counts by XRF to see how the ratio of barium and copper compares. In the Yale set, which is represented by the blue dots, we're seeing two groups of azurite being used. In the Morgan set, which is the red dots, comparatively, we have lower amounts of barium, or in some cases comparable. What this means is that there are different azurite mixtures being used within the same deck of cards, as well as between the two decks of cards. These different groups of blue paint could be reflective of the different sources of azurite, or more likely the different quality of azurite being used. That selectivity could be related to the higher quality of blues wanting to be saved for certain cards or for certain important features, such as gowns of central figures, whereas less important figures like borders might get a lower quality, but this is a feature we are still exploring. The green paints, which there are at least 3 types, used in the cards also show differences in the manufacture of the Yale and the Morgan decks. The Morgan or Colonna cards contain much more complex green pigment mixtures that contain mainly malachite, a copper-based mineral green, as well as blue and yellow pigments and carbon black and darker greens. And this can be seen in the micrographs of the King of Staves. And in contrast, the Yale or Modrone cards show green copper-based pigments primarily being used, but we have yet to identify the exact copper compound. And we have some examples from the male page of batons on the screen here. And in this case, you can also see an example of the green copper-based glaze in the hat of the page, which is seen on several of the Yale cards, but is not in the Morgan cards. And then, as Elena already mentioned, in both cases, lead tin yellow was mixed into the greens, especially in the green foregrounds, to make highlights of the grasses and flowers as decorations. And so you can see in the tin map the highlights for that lighter grassy region.
At the Metropolitan Museum of Art, we were able to apply an additional imaging modality to analyze the collection of Tarocchi cards from the Morgan Library, called reflectance imaging spectroscopy, or RIS, as Richard introduced. Similar to how digital cameras collect millions of pixels of color info to create the photos we see on a screen, this camera scans the surface of paintings to create 3D image cubes featuring millions of pixels with diffuse reflectance data in each pixel. Thus, each 3D image cube is a stack of images that we can visualize how materials absorb and reflect at hundreds of different wavelengths, and in this case, from 400 to 900 nanometers. But because the data dimension is so high, we process and reduce these image cubes through various analytical steps, including multivariate statistics, to extract the most distinct or unique signals, otherwise called end members, in the 3D cube. This here is a 3D visualizer representing the cube's data, and we select clusters from this pixel cloud that will define the unique spectral signals. These are denoted by the different colors, which in turn should represent artist materials such as pigments, both inorganic and organic colorants, as well as possible conservation interventions and degradation products. I'm going to present 2 examples from the Morgan collection to show how RIS aided our analyses of the cards. First, we'll look at the results from the King of Staves. From the statistical analysis, this list of spectral end members was extracted from the King of Staves. The x-axis on this plot is the wavelength, and all the end members are stacked here. So we don't see the absolute values of reflectance, but rather their relative intensity. The locations of peaks, absorptions, and inflections, which is a change in the slope of an increasing or decreasing curve in the diffuse reflectance spectra, correspond to various electronic transitions due to charge transfer, such as in iron ochres, DD orbitals, valence to conduction band transitions in semiconductor pigments, and those of delocalized molecular orbitals and dye-based pigments. For example, the bright red end member has an inflection halfway through the sharp rise at approximately 590 nanometers, which is an indicator for vermilion. So from this list, we can see that the card contains red and yellow ochre, green earth, azurite, smalt, folium, saponwood, copper green, and lead tin yellow. Now, while several of these were already identified or inferred by XRF, certain results stood out. Folium, a purple dye colorant, was first evidenced in the Morgan Library's collection of Tarocchi cards by RIS, which prompted further investigation and confirmation by other techniques. The flesh tones are often dominated by iron pigments and lead white, and usually include a semiconductor red such as vermilion. However, we also see the possibility of green earth in the face, as one of the end members, which has a green spectral profile, shows a bump in the reflectance slightly above 800 nanometers, characteristic of green earth. This would suggest the Verdaccio technique, where a green earth layer is first applied under the iron ochres for the facial execution. Smalt was inferred by the presence of cobalt and other minor and trace elements in the XRF analysis, and subsequently confirmed by Raman. RAS was able to independently confirm the presence of smalt, which shows a relatively rare and thus important use on illuminations in 15th century Italy. Through this non-invasive approach, we could identify smalt's 3 characteristic subbands from ligand field transitions due to the copper-2 ion at approximately 535, 595, and 645 nanometers. We use this extracted set of unique end members to compare to all the pixels in the image cube. Those within an assigned acceptable tolerance get labeled to an end member, and thus we produce a 2D material map showing how these end members are located throughout the image scene, or in this case, how the artist painted. For example, we can see the distribution of the different blues, smalt and azurite, in the border, cape, armor, and flowers. The layering of smalt and azurite was previously shown for the Last Judgment, and the RIS map for the King of Staves also shows where the pure and layered applications of smalt are. We also see that folium was applied as a top layer over sapon wood on the stockings to produce the gray purple tone. The other example I will show is of Temperance, one of the replacement cards in the deck from the Morgan Library collection. From XRF analysis, there was a preliminary understanding of the materials present in the painting. So we were aware that there were 2 distinct blues, one that was copper-based. We were aware of the presence of lead white and vermilion and lead tin yellow, and we knew that there were 2 distinct greens. However, there were still some open questions. We understood that there was the presence of an organic in red regions. It was yet unclear the nature of these greens. And while we were aware of certain materials being used and the presence of additional unassigned materials, we also wanted to see how they were being used. So, RAS analyses confirmed an insect-based red lake based on the location of the double absorptions at 525, 565 nanometers. And we could differentiate between different lead tin yellow applications in the painting, such as in the hair versus in the light green grass regions, but not in the dark green mountains. It supported the XRF finding of 2 blues. RS here could assign, however, the material nature of the second blue as lapis lazuli, as this pigment has characteristic absorption maximum at 600 nanometers and a rise in the reflectance in the red and IR wavelength ranges. Mapping showed how the artist used the materials identified in this list, such as lapis lazuli, exclusively to the jug in Temperance's hands, while azurite was used for her dress. Of course, the RS analyses don't stand alone. We want to emphasize the value of multimodal imaging spectroscopy in having both the elemental and diffuse reflectance maps, for we can ascertain many of the materials and their distribution by these complementary data sets. We saw how elemental maps of barium and copper suggested azurite, which didn't appear in the white and blue jugs. The RAS map, on the other hand, could identify and visualize both azurite and lapis lazuli. However, for the use of lead white, RAS was unable to confirm it from the Venaria data alone, but we could utilize the lead maps and corresponding XRD and Raman measurements to make that assignment. Thus, we can refine our search, maps, and interpretation of the painting materials by a multimodal imaging spectroscopy approach with additional point spectroscopy techniques, all of which together converge to more conclusive results. And though RAS was able to identify the presence of red lakes and purple dyes, and in some cases ascertain their nature to some degree, we required further confirmation. So techniques such as Raman spectroscopy became particularly useful in identifying the specific material nature of these pigments.
One of the greatest challenges in any scientific study is the identification of the organic dyes and pigments. These materials elude XRF and many other analytical techniques that are typically used in this type of investigations. And that is why we often need to remove very small samples to confirm their exact nature through analysis with microinvasive techniques. As we've seen earlier, we got a preliminary indication of the presence of organic reds and purples from hyperspectral imaging, and for insect dyes, also from Raman spectroscopy. SIRS is the technique that allowed us to confirm these results in a selection of cases where microsamples could be removed. In the Morgan Colleoni cards, we visually identified several organic pigments of a great variety of color shades, ranging from orange reds to delicate pinks, intense purples, and very distinct lilac grays. And you can actually see a selection of the observed colors on this slide. They appear to have been used both as paints and as translucent glazes applied directly on the metal leaf for an iridescent effect, or over the paint to outline, for example, fine details of the figure's garments and accessories. In the Morgan cards, we identified three main types of organic reds and purples. The most widespread is sappanwood, which we found in many of the figures' orange-red hats and garments, in the crowns and other elements with red glazes applied directly on the oro di metà, which we will hear about in a second, and on the back of the cards. In mid-15th century Italy, sappanwood was called verzino. It was extracted from a wood of reddish color belonging to the Cesalpinia sappan species, imported mostly from Southeast Asia to the markets of Western Europe and used extensively for the production of textile. Considering that the Tarocchi cards were meant for use rather than for display, it seems to actually make sense that the most common organic red present is a relatively cheap one, like sappanwood. The second type of organic red purple in the Morgan cards is kermes, extracted from the female of the Kermes vermiglio scale insect and native to the Eastern Mediterranean region. Unlike sappanwood, which was only detected on the recto of cards attributed to Bonifacio Bembo, we did find kermes both in Bembo cards and also in replacement cards like Temperance and Fortitude, where it's mostly used on figures' garments, gloves, shawls, and shoes, as well as on the purple cliff at the bottom of some of the cards. In replacement cards, kermes, which was a more expensive choice compared to sappanwood, is the only organic red identified on the recto, just like lapis lazuli seems to be predominant compared to the cheaper azurite. In the 1400s, kermes belonged to a group of colors named scarlatti, indicating cloths dyed with grana, and the term grana referred to kermes originated from the fact that the insects dried in the sun had a rounded shape that resembled small grains of wheat or sand. And the resulting kermes dyed clothlets really played an important role as luxury items on the international market. The third type of organic red or purple of a gray lilac color is folium, which is only present on Bembo cards. Folium was historically produced from a plant named Morella, native to southern France, corresponding to Chrozophora tinctoria and other botanical species. The berries of this plant produce dyes ranging from red to blue, depending on the pH, and the term folium was usually referred to the purple phase. The dye was stored in the form of dyed clothlets, and it's very interesting that its name actually originates from the practice of preserving the pieces of cloth between the pages of books, whose name in Latin was folia. Organic red pigments can also be observed in the Yale Visconti di Modrone deck. While the exact nature of these materials on the Yale cards has yet to be determined, we can definitely notice fewer shades compared to the Morgan cards, all very similar to one another. As some of you may know, organic dyes were often precipitated onto an inorganic substrate to increase their durability and color intensity. This process was referred to as laking, and the resulting pigment as a lake pigment. The macro XRF maps show the presence of potassium in organic red areas of some of the Morgan cards, which likely indicates the substrates that were used to make kermes and sappanwood lakes. A similar phenomenon can also be observed on several cards of the Yale deck. One such example is the 10 of batons. On the magnified area shown to the right of this slide, we can see a red transparent pigment outlining the knobs of the batons, but no pigment is visible in the area where thin lines were incised in the metal leaf to represent feather barbs. Yet, in the potassium map, we can clearly see brighter areas in the shape of feathers, likely indicating the presence of a lake pigment that has now disappeared. In terms of materials used as lake substrates, most historical recipes mention a mixture of alum and potash. Italy, with its volcanic soil, was particularly rich in rock alum, or allume di rocca, consisting of a potassium aluminum sulfate and often also aluminum hydroxide. Switching gears from the organic reds and purples, we also identified organic materials of different colors. For example, while most Morgan cards have red, blue, and black outlines typically next to each other or partially overlapping, certain cards display a brown outline, which was made with an iron gall ink. We also detected indigo on the dark shades and details of the figure's blue garments. And it's interesting to notice that several historical recipe collections include mentions of a Lombardian indigo, which according to experts would have indicated indigo that had been exported from India and brought through the region of Lombardia. If that was the case, the botanical source would be Indigofera tintoria, although the same dye could also be extracted from the woad plant or Isatis tintoria, which grows in many parts of Western Europe, including northern Italy. As far as the blacks are concerned, the pigment most commonly found in our selection of cards is a carbon-based black, identified on the fool's feathers, on time's hourglass, and on the dark shades and details of the figure's garments, as a more frequent alternative to indigo, especially on cards attributed to Bonifacio Bembo. We ran into the greatest analytical challenge when analyzing a black paint used to outline trees over a green background on one card from the Morgan Library, the chariot that you see here. XRF analysis didn't detect any significant element, pointing to a possible organic nature of this material. Raman, on the other hand, gave us a very complex spectrum in which we immediately identified indigo, which is the series of signals that are here marked in blue. To our disappointment, the rest of the bands didn't match anything in the available Raman libraries. In the same spectrum, we also got in a manuscript by Michelino da Besozzo that we analyzed for comparison, but that's another story. A little help came from FTIR of a similar area on a card from the Accademia Carrara, which was particularly rich in oxalates, as well as malachite from the underlying green paint. So going back to the Raman spectrum, we realized that 3 bands could be actually ascribed to mullite, which is a copper oxalate that may have formed from the degradation of the underlying malachite layer. As of today, the other signals remain unassigned, so I'm officially making an appeal to all Raman spectroscopists who are in attendance today. If you've seen the spectrum before or you have any suggestions, please do let us know. So here's the summary of the main results in terms of pigment identification comparing Morgan and Yale cards. In general, there are many similarities between the 2 decks, though the color palette of the Morgan cards appears to be more complex. Organic colorants like kermes, sapanwood, and folium have been identified in the Morgan cards, while the Yale deck includes fewer shades that are yet to be studied. In addition to azurite and lapis lazuli, the Morgan cards liberally use smalt as a blue pigment, either as an underlayer for azurite or in combination with the other inorganic blue colors. But there has been little or no smalt used in the Yale cards and no indigo as well. This absence of smalt carries over into the composition of the green pigments. In the Yale cards, green paints are unidentified, while main greens in the Morgan cards include complex mixtures of malachite and Latin yellow type 1 with azurite, lapis lazuli, and smalt. Latin yellow is the main yellow used in both decks, although the Morgan cards contain a second type of yellow-orange pigment based on yellow ochre. Browns in the Yale cards feature iron gall ink and some unknown brown colorant, while the Morgan cards also have mixtures of Latin yellow, vermilion, and carbon black, as well as mosaic gold, as we've seen before, only in the replacement cards. Finally, white and black tones include lead white and a carbon-based black for both decks, with the addition of indigo for the Morgan cards. In addition to studying the color palette, we've been gathering data on the binding media as well. FTIR analysis suggests the presence of both protein and polysaccharide-based media in paints of various colors, while the red glazes applied over the metal leaf or the oro di metà in certain areas contain mainly polysaccharides. This part of the work is currently in progress. We recently sent some microscopic samples from the Morgan and from the Carrara cards out to the Art Institute of Chicago, where their exact composition is being analyzed by PyGCMS and mass spectrometry-based proteomic techniques. So far, we've presented results mostly from the US phase of this research, focusing on the Morgan Colleoni and the Yale Visconti di Modrone cards. Thanks to the collaboration of Maria Cristina Rodeschini and Letizia Lodi, in the past few months, we've been able to expand this study to also include Tarocchi cards from the Italian collections. In February, a selection of 15 cards from the Accademia Carrara were sent on loan to our conservation center here at Venaria Reale for analysis. And in April, colleagues from the Morgan Library, Yale, and the Met visited us in Venaria to continue our joint investigation of the materials and techniques of the Carrara cards. And as you can see from the pictures, we also took a trip to Milano and Monza to see the Brera-Brambilla deck and to visit Olinda's chapel with the Zavatari mural paintings. Last week, I spent 3 days at the Pinacoteca di Brera with some of our portable instrumentation and officially began scientific analysis of the Brera-Brambilla deck. And a second in situ analytical campaign is scheduled for the fall. We are now in the process of working on the data, but what I can say is that we've already made some pretty interesting discoveries. A result that really stood out was the finding of a card in the Carrara deck, the 3 of staves that you see on this slide, that appeared to be made with different materials and techniques compared to the rest of the cards, possibly pointing to a different hand and time of production. For instance, as you can see from these micro photographs, there is no gold layer visible under the gold leaf. A pretty thick underdrawing is visible when examining the card under the microscope and with infrared reflectography. Unlike other number cards, which have a lead white background, this card has extensive calcium, but no lead at all. It is the only card in the Morgan deck, where in the Carrara deck, where organic yellows completely replace Latin yellow. Blues seem to be mixtures of azurite and indigo. Greens are also unusual, possibly mixtures of blue with an organic yellow. And while most stave and banner outlines are made with an insect red, there are a few retouches that are based on vermilion here. The back is also different, based on a mixture of vermilion and red ochre, while all other backs are painted with sappanwood. This was just a sneak peek into our current investigation of Carrara and Brera Tarocchi cards. There will definitely be more information coming out of this research, so stay tuned for more updates. And I think this is all for us. Thank you everyone for listening. We now have a break, and we'll see you back here at 12:30 Eastern Time or 6:30 p.m. Central European Time. Enjoy the break.